In the previous segment, we looked at various different sets: integers, pairs of integers, rational numbers, and the set of finite sequences over a finite alphabet, and determined that the cardinality was the same as that of the natural numbers, which means that all these sets are equinumerous and therefore countable. At this point, you might wonder whether that's it when it comes to infinity, and whether the subscript 0 to our aleph was perhaps slightly over-optimistic, and there really isn't anything beyond that number. Let us continue our investigation with sets of sequences as before, but with the difference that this time the sequences themselves are infinite. We shall represent an infinite sequence over a finite alphabet A simply as a function from the natural numbers to A. The natural numbers can be thought of as the indices into the sequence, so that 0 is mapped to the first symbol of the sequence, 1 to the second, and so forth. This time, of course, there is no empty sequence, since all these sequences are infinite. Since the infinite sequences in A are the functions from n to A, the set of all such sequences can simply be written as A to the n. For example, if A contains only one element, for example the dot, then A to the n also contains just one element, namely the function that maps every natural number to that one symbol. On the other hand, if there's more than one symbol, for example 2, then A to the n becomes infinite, which means its cardinality is at least aleph 0. Note that sometimes the digit 2 is used as a shorthand for the set of two elements, especially when the exact nature of those elements isn't important. Here we shall use 2 and the set containing 0 and 1 interchangeably. Remember from the first lecture that 2 to the A was an alternative syntax for the power set of a set A, and also that in lecture 3 on functions, one way to write the set of all functions from A to B was as B to the A. There's a very close relationship between the subsets of a set A and the set of Boolean functions on A, that is, functions from A to a set of two values. It is so close, this relationship, that sometimes people do not even distinguish the two. In Clojure, for example, you can use an object representing a set simply as a Boolean function. There's a fairly straightforward one-to-one correspondence for any set A between the set of all its subsets, its power set, and the set of all functions from A to 0, 1. And it looks as follows. Given an infinite sequence of zeros and ones, you can construct a set of natural numbers by including exactly those numbers whose position in the sequence contained a 1. Conversely, given a set of natural numbers, you can construct a sequence by making those positions 1 whose indices are in the set and all others 0. Such a function is also sometimes called the characteristic function of the set it was created from. So for example, for a small set A, this is what some of its subsets and their characteristic functions look like. This extends without any problem to infinite sets. With this, let us now look at the cardinality of 2 to the n, that is, of the set of all functions from n to the set of 0 and 1, or equivalently, as we now know, the cardinality of the power set of the natural numbers. We do this by following a famous proof by Georg Cantor, who used it to demonstrate that 2 to the n is not countable. The proof proceeds by assuming that it is, and then producing a contradiction. So let's start by assuming that 2 to the n is in fact countable. That is, that it is equinumerous to the natural numbers. If it is, then there must be a bijection between n and the set of all functions from n to the set 0, 1. Let's call that bijection f. Remember that a bijection is also surjective. That is, it maps to every element in its codomain, in this case 2 to the n. This is how we can represent f as a table of infinitely many rows and infinitely many columns. Each row corresponds to the one mapping by f to an infinite sequence. The row labeled 0 maps 0 to the sequence following it, then the row labeled 1 maps 1 to the sequence, to its sequence, and so forth. Each of those sequences itself is a mapping from the natural numbers to 0 and 1. So the column headings contain the natural number indices into the sequence, and then the cells in the table contain the corresponding 0 or 1 that the corresponding sequence maps them to. Note that for this example, the actual zeros and ones inside the table do not matter. What does matter is that every sequence in it is different from every other in at least one position. With such a table representing the f we postulated as our bijection, we can construct the diagonal sequence of f, which we call d. It too is of course an infinite sequence, and its ith symbol is the same as the ith symbol of the ith sequence in the table representing f. Using d, we can build an inverted diagonal sequence d bar, which is 0 whenever d is 1 and vice versa. The crux of this proof is to realize that this inverted diagonal sequence d bar is different from every sequence in the table, because if the ith sequence had 0 in its ith position, then d bar will have a 1 and vice versa. In other words, d bar does not occur in the table as a sequence that is being mapped to, which means it does not occur in the range of f. And that in turn means that f cannot be surjective, which means it also cannot be a bijection, which contradicts the assumption of this proof. What that means is that no matter which f we choose that maps n to a set of infinite sequences of zeros and ones, we can always construct a sequence it does not map to. So it can never be surjective, and therefore it cannot be bijective. There is, in other words, no bijection between n and 2 to the n, which means those two sets are not equinumerous. So to summarize, we know that there are at least as many infinite sequences of zeros and ones as there are natural numbers. But we cannot construct a bijection. Therefore, there must be properly more infinite sequences of zeros and ones than natural numbers. Or, in other words, aleph 0 is strictly less than 2 to the aleph 0. So we have just discovered a new transfinite cardinal number, which is 2 to the aleph 0, and it's called C. The name alludes to the continuum, a reference to the real numbers, which also have this cardinality. Incidentally, a different basis does not change this cardinality. There are as many infinite sequences of zeros and ones as there are infinite sequences of, say, characters of the alphabet. Coming back to the problem from the first segment, let us now compare the size of the sets involved. First, how many programs can there be in any language L? Well, since L is a subset of some A star, it is countable, so its cardinality is at most Aleph 0. How many Boolean functions on the natural numbers are there? Well, as we just saw, the cardinality of that set is C. And what does that mean for our problem? It means there cannot be a programming language that would allow us to express all Boolean functions on the natural numbers. There simply are not sufficiently many different programs so that all such functions could be expressed by a different one. In point of fact, Aleph 0 is actually tiny compared to C. One might say it is so infinitesimally small in comparison that almost none of those functions could be written in L, no matter what L is. Let's quickly talk about the real numbers to wrap up our discussion of sets of numbers. It shares with the rational numbers that it is dense and that every non-empty open interval of real numbers is equinumerous to the entire set R. This allows us to determine the cardinality of R by looking only at, for example, the real numbers from 0 to 1, for example, in the form of strings of decimal digits. The one thing we need to ensure, however, is that we do not count numbers more than once. For real numbers that have two equivalent forms, for example 0.5 and 0.49 repeating, we need to drop one of them. In this case, the terminating one, 0.5, that ends with infinitely many zeros. This makes the proof technically slightly cumbersome, but as it turns out, the real numbers still end up with cardinality C. In fact, what we demonstrated was that for a countable set, the cardinality Aleph 0 of that set was strictly smaller than the cardinality 2 to the Aleph 0 of the set of functions from that set to the set 0, 1, which is also the cardinality of its power set. It turns out that this is true in general, for all sets of all cardinalities, big or small, finite or infinite. The cardinality of any set is always strictly smaller than that of its power set. Or equivalently, for any cardinal number C, finite or transfinite, C is always smaller than 2 to the C. What does that mean for transfinite cardinal numbers? Well, it means there are infinitely many of them. I want to conclude with a few comments on transfinite cardinals. So far, we have encountered two of them, Aleph 0 and C, which is 2 to the Aleph 0. We also know that there are infinitely many transfinite cardinal numbers. They are, in order, a chain of Alephs starting with Aleph 0 such that between any two consecutive Alephs there is no other cardinal number. So it seems natural to ask, where does C, that is 2 to the Aleph 0, fit in? It is greater than Aleph 0, but is it the next one? Is it Aleph 1? Or are there sets of a size between Aleph 0 and C. This was an open question for a good long while, and the idea that C is in fact the next transfinite cardinal after Aleph 0, that it is Aleph 1, became known as the continuum hypothesis, or CH for short. Paul Cohen showed that CH is in fact independent of the common system of axiom for set theory. What this means is that neither it nor its negation can be proven from those axioms. In other words, we do not know how big Aleph 1 is, and there's actually no way to find out. Since we cannot properly know the size of the Alephs, people introduce cardinals named Beth 0, Beth 1, etc. So that Beth 0 is the same as Aleph 0, and every subsequent Beth is 2 to the power of the previous one. Therefore, C is the same as Beth 1.